Oh, hello and welcome. This is SFU Math 232. My name is Brenda Davison. We're going to cover today section 3.6, Matrices with Special Forms. Okay, so some interesting things here, and again, some vocabulary that we're going to have to get used to. Okay, so if we see a matrix that looks like this one here, D, where all of the entries off the main diagonal are 0, we call that a diagonal matrix. Okay, so here's an example, 3 by 3 diagonal matrix. You can see that these guys are all zeros, and the diagonal entries on the main diagonal are not 0. They are D1, D2, and D3. So let's just write what the inverse of this matrix is. And I'll do it by the way that we have found matrices in the previous section. It's not going to take very long. So we would take the matrix for which I want to find the inverse. And then I write that as a compound matrix with the correct size identity matrix. And I perform row operations until I have this thing, row equivalent to the identity matrix. And then I can do all of those row operations at the same time. I'm going to divide row 1 by D1. I'm going to divide row 2 by D2. Row 3, I'm going to divide by D3. There it is. Okay, so now I know that the inverse matrix of the diagonal matrix looks like this. So if ever I see a diagonal matrix and I want to know what the matrix is, I can simply write that down. Of course, we do have to have the restriction here that D1, D2, and D3 are not 0. Okay, what would happen if I then tried to take a power of the matrix, d cubed or d to the 5th or something like that? Let me do d squared, so we'll be able to see from that what happens. So d squared, that'll be d times d. So that here's d, and I'll multiply that by d. Like that. I'm just going to perform that multiplication, taking that first row into the first column, like that, and I'll get this here, d1 squared, 0, 0, 0, d2 squared, 0, 0, 0, d3 squared, like that. Okay, now you can see if I then multiplied again, I would get d cubed. It's not hard to see what's happening here. So in the general case, d to the k will be this here, d1 to the k, 0, 0, 0, d2 to the k, 0, and 0, 0, d3 to the k. Okay, so it's easy to take powers of matrices that are diagonals, easy to find the inverse. Okay, next thing we'll just take a quick look at, what if I just take any 3 by 3 matrix and I multiply on the left by a diagonal matrix and I multiply on the right by a diagonal matrix. Let us see what happens. So I'll go d times a, and that will be d1, 0, 0, 0, d2, 0, 0, 0, d3. And I'll multiply that by a, which is a11, a12, a13, a21, a22, a23, a31, a33. Okay, I do that multiplication. I get d1, a11, and I get d1, a12, d1, a13. So you can, perform this multiplication yourself. Don't just copy me doing it. We know how to multiply matrices, so perform the multiplication yourself, and you will get this here. So basically the elements in the first row of A are multiplied by D1. The elements in the second row are all multiplied by D2, and the elements in the third row are all multiplied by D3. Like that. Okay, then what I'm going to do is do it the other way around. I'm going to multiply A times D. So I'll have to put A here. A11, A12. I'm going to multiply by D. And what happens, it doesn't come out to be the same. What happens is we have all of the elements here multiplied, all the elements in the column are multiplied by D1. And then in the first column, then all the elements in the second column are multiplied by D2. And all of the elements in the third column are multiplied by D3. Okay, so just to draw attention to the fact that AD is not equal to DA. And you'll notice what's happened is this all multiplied by D1, and then in this case, all multiplied by D1. So again, you could do this quite quickly once you see what's going on. It's generalized to the n by n case. We just sort of did everything in an example 3 by 3 so we could see what's going on. That's a diagonal matrix. Okay, next type of matrix we're gonna see is the triangular matrix. Okay, and we're saying here we're starting with a square matrix, and all the entries above the main diagonal being 0 is called lower triangular, and a square matrix in which all the entries below the main diagonal are 0 is called upper triangular. So this one here is at the first one, this guy. This one is upper triangular. Okay, basically the numbers are up here. That's the way I remember it. And then this one here is lower triangular. The numbers are in the lower half, or lower, I don't know, it's not really half, but okay, lower triangular. Okay, so you can express this algebraically. A is upper triangular if A sub ij is 0 for every I greater than j. And it's lower triangular if A sub ij is equal to 0 for every I less than j. Can a matrix be both upper and lower triangular? Answer, yes. Identity matrix, for example, satisfies that property. A diagonal matrix satisfies that property. Okay, it's upper and lower triangular. Okay, next on our agenda is to just take a look at a few of the properties of the triangular matrices. So here they are here. We have two matrices, U, which is upper triangular, and L, which is lower triangular. And then U transpose is lower triangular, and L transpose is upper triangular. Okay, if we've got two matrices that are upper triangular, then the product of the two of them is upper triangular. If we've got two matrices that are lower triangular, the product of them is lower triangular. This is triangular. If a triangular matrix is triangular matrix is invertible if and only if all of its diagonal entries are all non-zero. And the final one here, if the upper triangular and lower triangular matrices, let's see, hang on a sec. If U and L are so that's right. I misread myself. Okay, so if U is upper triangular and it's invertible, and L is lower triangular, also invertible, then the inverses are respectively upper triangular and lower triangular. Okay, so we're just going to prove 1 and 2. By that I mean actually A, the first two, and B. We'll prove A and B. C is, of course, similar to B. C is similar to B, and C is done in the textbook. D and E are going to come later. Okay, so let's take a look at A. It's basically saying that if we have a matrix, just as an example here, if we have a matrix A that is upper triangular, let's gonna draw that 1, 2, 3. This is a upper triangular matrix, and then I take the transpose. I get so it's saying here that this one here is upper triangular, and then when I take the transpose, I get something that is lower triangular. Okay, so I mean, I'm just going to say proof of this is that transpose reflects the entries. That's across the main diagonal. Okay, so I mean, given A such that Aij is 0 for every I greater than j, that's our upper triangular matrix, then A transpose has Aij equals to 0 for I less than j. That's what happens during the transpose operation, and that is in fact what it is to be lower triangular. Okay, so this statement is saying given that A is upper triangular, then that's what this means, and then we do the transpose and we get this, and we're like, hey, that's what it means to be lower triangular. So that's it, we're done. That is the end of A. So A transpose is lower triangular. Okay, how about part B? Okay, given U1, U2, upper triangular, and we're going to be multiplying these together. So let's take a look at the ith row of U1. The ith row of U1 looks like this. There's some number of zeros, and then the first non-zero entry is going to be AII. That's the one on the diagonal, and then AI, I plus 1, etc., all the way to AIN. Okay, and then let's take a look at the jth column of U2. It's also upper triangular, and that means that the jth column will look like this. It will have some numbers in there, BJ1, BJ2, etc., like that, all the way down to BJ J minus 1, and then it'll be BJJ, and then after that there'll be some host of zeros, depending on which row we are in. I'm sorry, which column we're in. Okay, so now let's form the product U1, U2, and look at the ijth entry. That is going to be the ith row of U1 multiplied by the jth column of U2. And that's going to be equal to 0 if I is greater than j, because you have zeros here at the beginning and then you have zeros here at the end. Okay, so we can see when this is going to be 0. So this means all the entries below the main diagonal are 0. Up, there you go. The product U1, U2 is upper triangular. Okay, that's so we've seen diagonal matrix, upper triangular, lower triangular. Now here's some more special types of matrices, symmetric and skew-symmetric. So a square matrix is symmetric if it's equal to its own transpose, and it's skew-symmetric if the matrix is equal to the negative of its transpose. So we could say that this way: it's symmetric if Aij is equal to Ji, and it's skew-symmetric if Aij is equal to minus Aji for every I and j. Okay, so let's just give a couple of examples here. 2 by 2 example. Here's a matrix. that matrix is symmetric. Okay, you can see that if I take the transpose, I will get exactly that back. Okay, and here's one that is skew-symmetric. Let me just, A1 is symmetric, A2 here is going to be skew-symmetric. That's going to look like this. Okay, so if I take the transpose and then I take the negative, I will be back to where I started. Okay, so if we have A and B symmetric matrices with the same size and we have some scalar, then the transpose is also symmetric. The sum and differences of the two of them are symmetric, and the multiplying by a scalar it remains symmetric. So just some properties of the symmetric matrices. And here's another theorem. The product of two symmetric matrices is symmetric if and only if the matrices commute. So let us prove this one. We're given A and B symmetric matrices. So let's do the proof in this direction. We have A, B symmetric matrices. Okay, and what we do is we want to then, going in this direction, assume that AB is symmetric. And we want to, so our idea now is, this is what we want to do. We want to show that AB is equal to BA, the matrices commute. Okay, so let me take a look at AB transpose. AB transpose is equal to B transpose A transpose. That's a property of the transpose. We saw that a few lectures back. And then that is equal to BA, because B and A are both symmetric. Okay, but we have that AB transpose is equal to AB. Why? Because AB is symmetric. So here now we have on the left side AB transpose and AB transpose. Those are equal. So that means the things on the right side have to be equal. And we have that BA is equal to AB, and the matrices commute. All right, so that's in one direction. Now we're going to go in the other direction. We still have AB are symmetric, so that's still the case. AB are symmetric matrices. And now what we do is we assume the matrices commute. And we want to show that AB transpose is equal to AB. That's what it means to be symmetric. The product would, if I take the transpose of the product, it's equal to the product. Okay, so let's start with what we're told. We're allowed to start here. AB is equal to BA. I'm going to take the transpose on both sides. Okay, and then this one here is A transpose B transpose, and that is equal to AB. So I have showed that right here that AB transpose is equal to AB. That's what I wanted to show. AB transpose is equal to AB, and we're done. Okay, the product is symmetric. AB is symmetric. Okay, so that's totally straightforward. We just have to remember that in both of these we use this property of the transpose that we saw earlier. Next, if A is an invertible matrix, then the inverse A is invertible and it's symmetric, then the inverse is also symmetric. Okay, so we're running this one under the assumption that A has an inverse. So I'm going to take that inverse, there it is, A is invertible, so it has an inverse. I'm going to take the transpose of that. And we know already that this is equal to this because, well, I'll even say what it, whoops, that's not what I wanted to do. Hang on, let's fix that. Right, there's a theorem we saw earlier. I'm just going to refer you to the textbook page for that. It's sort of this here is a theorem that is in our Busby textbook. That's page 104. Okay, so we have that, and then now we can say that this is equal to A inverse because A transpose is equal to A. So this is because A is symmetric. So we have now shown that A inverse transpose is equal to A inverse. That's a definition that is telling us that A to the minus 1 is symmetric. Okay, so let's just take a look at a few matrices so we can identify the structure that they have. I'll just sort of go through these in order. So I'm going to identify, I'm just going to sort of draw a line. There's the main diagonal. I see that everything below the main diagonal has zeros in it. So this one here is upper triangular. Okay, this one is upper and lower triangular, and it is also, we would say this is diagonal. It only has entries, only non-zero entries on the diagonal. Let's take a look at this one here. I see that it is equal to the, well, I see that this one is the negative of this one, and I may take the transpose and then take the negative of it, or I may be able to see right away that this one here is skew-symmetric. Okay, let us watch this one here because it looks a little bit similar. We've got the main diagonal, and then you can see that you've got a transpose looking situation here, in that we've got BC here and minus B minus C here, and the E and the minus E. It looks pretty good. It looks almost like this, but the problem is if you take the negative transpose, you're going to get negatives here where there are not negatives here. So this thing we are not going to identify as skew-symmetric. This doesn't have any structure that we have been discussing. Similarly with this one, it's the wrong diagonal. We're always looking at this diagonal here. Okay, so there's nothing here either. And then in this one here, let's take a look here. So I'm not sure why this thing is moving. Sometimes when I'm putting my hand down, I must be bumping something. Okay, so there, this one right here. So I identified this here as none, and here as symmetric. Okay, so we have a question here. Generic 3x3 symmetric matrix has 6 degrees of freedom. Okay, what does that mean? That means there's 6 things that you can change. Let's just draw out the matrix and show what that looks like. A, B, C. That's the diagonal. It's a symmetric matrix. So what is here is also going to have to be here. And what is here is also going to have to be here. And similarly, here and here are going to have to be the same. So there is the general case of the 3x3 symmetric matrix. There is 6 possible things I can change. I can change A to whatever I want independently. I can change B. So that's what this is telling you. There's 6 items here that you can change. There's not 9 because of these ones. That is one choice. I mean, I pick D. It goes in 2 locations. Okay, so I am noticing that how many degrees of freedom do I have? I'm looking at this. I have this is how I'm thinking of this. When I put something in onto this first row, I use 3 symbols. And then when I put something in on the next row, I have to already reuse the D right here. So nothing new is going to happen. And then here I put in 2 symbols. And then on the last row, this thing is going to be the same as something I've already put in. And this entry is going to be the same as something I've already put in. And so I'm putting in 1 new thing. So that is where my 6 degrees of freedom is coming from. So what I'm recommending you do right now is do the 4x4, do the 4x4 case. Convince yourself that your degrees of freedom for the 4x4 case looks like this: 4 plus 3 plus 2 plus 1. And then allow yourself then to generalize how many degrees of freedom does the n by n one have, and then that is going to be the sum of I equals 1 to n of I, and that is n times n plus 1 over 2. Okay. And then again, I'm going to leave this as an exercise. What happens in the skew-symmetric case? So try this out as an exercise. Exercise is good for you. So think maybe before you start, do I have more or less degrees of freedom in the skew-symmetric? Particularly think about those diagonal entries. Okay, we've already actually seen this in one of our exercises when we introduced the transpose a little bit earlier. We multiplied together A transpose A and A transpose, and so I'm just gonna, I don't know if it was lecture 7, actually. I'm not happy with that. Let's just say previous lecture. We have seen this though, previous lecture. So we saw what could happen if we have an n by n. Let us take an A is, well, let's say A is m by n. Then if I take A, m by n, and I multiply by A transpose will be n by m. That is going to leave me with a product that is of size m by m. Similarly, if I take A transpose, which is still n by m, and I multiply by A, which is still m by n, I will get a product, A transpose, which is n by n. So that's what this is saying here. A transpose is n by n, n by n, and A transpose is m by m. Okay, let us think of A as being a list of column vectors. So I'm thinking in this case of A like this. One column vector, a second column vector, etc., like that, columns of A. And then we can think about, well, what would A transpose look like? A transpose would then look like this. Those things would be row vectors, like that. So I would take the transpose of that first column, A1, that vector A1, and I would take the transpose and it would become the row of A transpose. And then I would do the same thing. The next one, A2 transpose, like that. That would be the next row, and I would go all the way down and I would have AN transpose, maybe like that. Now I'm going to consider what happens when I multiply those two things together. And so I would take the first row of A transpose and I take that into the first column of A. And you can see quite handily when you do that, maybe if you need to concoct for yourself an example, but hopefully you can see here that this then looks like this. The first entry here is going to be the dot product of A1 with itself, and then the next one will be the dot product of A1 times A2. We'll go the whole way across. This will be A1 dot AN, and then we'll come down to the second row, A2 dot A1, A2 dot A2. We'll go the whole way across AN, A2 dot AN, and then we'll go down to the next one. We'll keep going, and then finally this last row will look like this dot product here. So it's a whole array of dot products. There we go. Okay. Here's another theorem. If A is a square matrix, always be careful to sort of read what the hypotheses are. Then these matrices A, A transpose and A transpose A are either all singular or all invertible. That means that either all three of those matrices have an inverse or all three do not. So I'm just going to sort of wave my hands around here with this theorem. I'm not really going to provide a proof, but I'm just going to sort of give an explanation of why this must be. So we've already seen this. If A is invertible, that implies that A transpose is invertible. And then if we take a product of two invertible matrices, we get something that is invertible. So I mean here that implies A transpose A are invertible. Okay, similarly, if we just chose one of them sort of to be singular, let us just say that A transpose was singular. What would that mean? That would mean that, well, it means at least one of them has to be singular. A would have to be singular, or A transpose would have to be singular. That would immediately imply, of course, putting those two things back together, that A transpose A was singular. Meanwhile, we have this situation where we already know if that one's singular, then that one has to be singular, and if that one is singular, then that one has to be singular. So they all are. Okay, that is that. Okay, now we're going to come up with something that looks maybe a little bit different. I think this is actually the most interesting part of this section of the text that we're in, 3.6. So we're going to take a look here at matrices of this form I minus A. These come up in economics, in engineering. These are, it's not just a sort of invented thing like, can we just say something about this? No, it's because it comes up in this context of a fixed point. So let's investigate what that is, or remind ourselves if you've seen this before. So in the context of linear algebra, we're calling here a vector x is called a fixed point. So the vector is called a fixed point of the matrix if ax equals x. Or equivalently, these two things mean the same thing. Ax equals x, or I minus ax equals 0. So let us just make sure we understand why that is the case. We have here ax equals x. And then I can go 0 equals x minus ax. And then I can factor that. Okay, and then I have what's written there. Okay, so that is, those things are equivalent. Okay, what does it mean fixed point? So fixed point comes up in functions too. So a fixed point means where you end up with f of x equals x. Okay, so let us just get an example here. A fixed point, say, let us consider the function. This is now in the function world. There's fixed points there as well. So if we have a function like this, f of x equals x squared, we could ask for what x does f of x equal x. And then I can figure that out. For what x does f of x equal x? That would happen when x equals 0 and x equals 1. I mean, I have, for this function, f of 0 is 0. 0 is unchanged. F of 1 is 1. The 1 is unchanged. So by operating on 1 with this function x squared, nothing happens. This is the same idea that I'm having here. I'm going to try to find a vector x such that when I operate on x by a, nothing happens. I just get x back. So I'm going to write that out in words. This is when it says find the fixed points of A. I'm asking for what vector x does ax equal x? Which means, in some ways, for which vector x does A do nothing to x? So we already know ax equals x is equivalent to writing I minus a x is equal to 0. So I'm gonna compute this I minus a for this matrix here, A. So that is like this. I minus A, like that, X equal to 0. Okay, so that is, I do this computation here, and I find that I have this 0, 0, minus 3, minus 1. Okay, I can now put this into an augmented matrix and put it into reduced row echelon form, and then I will be able to answer the question what x1 and x2 makes this true. And so I do that, and I find out that I have a free variable, x2 is free. So I'm going to put x2 equals to t, and then I find out, looking at this here, that x1 is minus 1/3 t. That gives me the vector x1, x2 to be equal to t minus 1/3 and 1. So I am saying that this vector right here that I just calculated, that vector is a fixed point of the matrix A. Let's see if it's true. Okay, that to be a fixed point means I take the matrix A, I multiply it by the vector X, and I expect nothing to happen. So let me make this calculation. I take the first row into the column. I get here minus 1/3 t. I take the second row. I get 3 times minus 1/3 is minus 1t plus 2t. That gives me t. So this is exactly the same as this. So applying this matrix here, using this matrix operating on this vector here does absolutely nothing. I still get the same thing back. Matrix did nothing. That is a fixed point. So we can calculate those for matrices in the manner just described. Okay, there's more exciting stuff, and that is you will recognize this identity for regular numbers, for x a real number, and k a natural number, so a positive integer. Okay, so this also holds for matrices, where I mean I is sort of I is 1. I is the equivalent of 1 in the numbers, and x is a. Okay, so that same exact identity holds. Now let's imagine the case. Imagine the case that if we have the case, this doesn't have to happen, but if ak is equal to 0 for some k. So we can take a, and then we could take a squared, and maybe not all the entries are 0. Then we could take a cubed, and maybe not all the entries are 0. But we imagine keeping doing this until we get to the time when we do a to some power k, and we find all of the entries in the matrix are 0. If that happens, then we have the situation like this: I minus a times I plus a squared plus ak the minus 1 is equal to I. Why is that exciting? Because that tells you that this matrix is the inverse of this one. Because when I multiply them together, I get the identity, and that's what it means for something to have an inverse. It means when you multiply something by something else, if the result of that is the identity matrix, then you have found the inverses. So the product here is I. Therefore, 1 minus a to the minus 1 is this thing. There it is. So I mean, I could find I guess I can find the matrix this way, the matrix inverse this way if I wanted to. Okay, so that's what this is saying here. Is exactly what I just wrote. It's this stated as a theorem. So if a is square and a k equals 0 for some suitable positive integer, then this guy is invertible, and his inverse is this. Okay, if we're in this situation, okay, so some vocabulary sort of this. If k, a to the k, equals 0 for some k, then A is called a nilpotent matrix, and k, then the k is the smallest, in this case, k, for which this happens, for which ak is 0. So you find the smallest value of k for which ak is equal to 0. And under that condition, k is called the index of nilpotency. Okay, there's just a couple of more things here like to mention, and that is, so we're not going to ask you to invert a minus I on an exam using a power series. Okay, but I want to point you to this because it's pretty interesting. You will recall for numbers that are between 0 and 1, this is important, for numbers that are between 0 and 1, then this situation, this is a true statement. Okay, this is the convergence condition for the sum of the geometric series. That's what we have here, the sum of the geometric series. You can check this if you want, for example, by taking 1 minus x and dividing that into 1 and saying how many times does 1 go into 1? 1 time, 1 minus x, subtract x. How many times does 1 go into x? X times. X minus x squared, x squared. How many times does 1 go into x squared? You get the idea. Okay, so you can show this by long division, and it is also the case that doing exactly the same thing where I plays the same role as 1 and the variable x is now been replaced by the matrix A, that we have exactly the same identity to the in the matrix case. Okay, and there's a little bit of a caveat here. There needs to be some suitable hypotheses on the matrix. Okay, again, we see that we've got a product of one thing with another, and it is equal to I. So these things are inverses of one another. So the inverse here of I minus A is a infinite power series of the matrix. Okay, so that's what the theorem is saying. If A is an n by n matrix, and here's the hypotheses for which the sum of the absolute values of the entries on each column or row is less than 1. That's the convergence condition. Then I minus A is invertible, and you can express it as a power series. Now, we are able then, in a computing perspective, to do this. I minus A to the minus, sorry, let's get the brackets in there. I minus A to the minus 1 is approximately equal to, and you can just take some number of terms here, as many as you want, but then you can stop and say that, well, I mean, yeah, and you have some error, right? You just cut off at a certain point, and you have some error, but the error tends to 0 as k tends to infinity. Okay, so I mean, you could determine what sort of error you are needing and that is permissible in your application, and then you could use this method to make that calculation and simply terminate at a certain point. So this is useful for numerical calculation when you want to find something within a certain error bound. Okay, so some special types of matrices, a couple of new vocabulary words, and then the fact that some of our operations that are much easier when we have a special type of matrix. And that is all for the special matrices. I will be back, section 4.1 shortly. Thank you. Bye.